Now that we've seen a number of ways to load our data into this common RDD abstraction, let's take a look at how we can glean meaningful information from it. As we've already discussed, a Spark RDD has two types of methods: transformations and actions. In this section, we'll focus on the former. A transformation is exactly what it sounds like: a method used to take our existing data set, run it through the provided function, which transforms the data into another shape. If you're ever trying to figure out if an RDD method is a transformation or not, simply take a look at the return type signature. If it returns another RDD, then it's a transformation, lazily building up the graph of operations to be acted on via an action. We've already seen the most basic of transformations while working through the word count code, map. In fact, a number of the other transformations we'll be seeing could be implemented through a map, albeit more verbosely. The imagery we just saw was actually a pretty good summation of map, where we execute a provided function against each of the items in our collection, using the results to output a new collection. For a more in-depth description of map, you can head over to my Scala course. The Building Blocks module has a section named Mapping the Data. You can see its use in our updated application. First, to convert our Hadoop data into a native string. Recall that in the last section, this was suggested as a first step if working with a Hadoop RDD. Next, we take this stringified data and use Scala's native XML support to parse out the text portion of Wikipedia's XML dump, using a custom parser to remove as much of the markup noise as possible. This leaves us with a collection of Wikipedia pages in their raw text format. Next, it'd be nice to tokenize our text into a collection of words. Again, this is something we've already seen in our word count example, through the usage of another transformation method, flatmap. This method is very similar to map, except it expects an array-like structure outputted from each of the transformations, which split does, as it returns an array of strings, representing the separate words of the wiki text. Flatmap takes this series of arrays and flattens them into one large array, thus the name flatmap. So, instead of a collection of collections, we end up with a single collection of strings. Next, we go back to our trusty map method to remove some stop characters from the words. This makes it so that we don't end up with words that contain a period or question mark or something similar. You might have already noticed our next transformation method, exhibiting a benefit of transformations returning other RDDs. It allows us to chain transformations one after the other, as we've done with this filter method. All filter does is take a predicate function which evaluates each item and determines whether the item should be kept in the final output or not. Here, we've provided a method that takes each word and only passes it to the final output if it's more than 2 characters long. This map followed by filter provides us with the more important words in the wiki pages. Next, we'll take a look at the unique words in our dataset using the distinct method, which goes through the collection, only keeping the first instance of each word, dropping any duplicates. This utilizes the object's hash and equality methods to find matching elements, as do all RDD comparison-like methods. Once we have our set of words, we'll use the sort by method to, you guessed it, sort. This method accepts a function that returns a value that's used to be sorted against. In our case, the word length. There's a default sort of ascending, so we'll be explicit and set this to false in order to get the larger words first. After all that, I'd like to take a look at a sample of our data instead of the whole thing. Normally, we just take a subset of the data, but Spark provides a convenient transformation method aptly named sample, which means the sample data will not be pulled back to the driver as other options would normally require. This can be nice when working in the shell or as part of a machine learning algorithm. It requires 2 parameters, one for the percent of the collection that should be sampled, ranging from 0 to 1. We're opting for only 1% of the data, and the with replacement parameter is there for distribution bias. If set to true, the sample size will remain constant for each piece of data pulled. However, this also means that you could end up with duplicates. We don't need our sample values to be independent, so we'll set this to false. That way, once an item is sampled, it's removed from the possibility of being selected again. Now, we'll collect our data and see how our data looks. We'll run our SBT assembly command to build the Uber jar as discussed earlier. Once that's created, we'll submit our Spark job just as we did with our word count app. And looking at our data, it seems like there's blank spaces and words with lengths less than our filter. That doesn't seem right. Back at the code, I've made use of the keyBy method to change our data into a key value pair, with our key being the token length, while the value is simply the original item, the token in our case. We'll see if this sheds any light on our problem. But before seeing this change in action, I wanted to point out a similar method named GroupBy. This method is very similar to keyBy, except instead of simply adding a key to the dataset, it also finds all other items with the same key, resulting in the value being a collection of these items. However, that means that all partitions must be reviewed and rearranged to accomplish this, a very expensive task. So, unless this is the final form for your data, the typical suggestion is to use other methods where possible. We'll see a number of these alternatives in the upcoming sections. Now that we've reassembled and rerun the updated code, our change has indeed revealed the problem. The filter is working as we expected. It only appeared that short and empty words got through because there were errant newline characters, which we can simply fix by splitting via a regular expression for word boundaries instead of a single space. Which again, reassembling and rerunning the code shows this fixes the problem.